Structure of atoms. Every atom is composed of a nucleus and one or more electrons that orbit the nucleus. The nucleus is a very dense region consisting of protons and neutrons at the center of an atom. So atoms and hence our matter consist principally of three fundamental particles: electrons, protons, and neutrons, which are the basic building blocks for atomic structure. Knowledge of the nature and function of these particles is essential for understanding chemical interactions. The relative masses and changes of the three fundamental particles are shown in the next table. You can see it. This one. The mass of an electron is very small compared with the mass of either a proton or a neutron. The change of a proton is charge of the proton is equal in magnitude but opposite in the sign to the charge on the electron. Modern measurements show that atom has a very small diameter, approximately 10 under the power of -10 meters, and the nucleus has a diameter about 10 under the power of -14 meters. It's difficult to imagine from these numbers alone, just how small the nucleus really is. For comparison purposes, if the atom were a size of a large stadium, the nucleus would be approximately the size of a small pier in the center of playing field. No, like in this picture, you can see the atom, the nucleus. Elements differ from one another according to the number of protons in their atom's nuclei, a value called the element's atomic number, or letter Z. That is, all atoms of a given element contain the same number of protons in their nuclei. All hydrogen atoms atomic number 1 have 1 proton. All helium atoms have atomic number 2, have 2 protons. All carbon atoms atomic number 6, because they have 6 protons, and so on. In addition, every neutral atom contains a number of electrons equal to its number of protons. The mass number is the total number of neutrons and protons, collectively referred to as nucleons, present in the nucleus of the atom of an element. Except for the most common form of hydrogen, which has 1 proton and no neutrons, all atomic nuclei contain both protons and neutrons. In general, the mass number is given by like sum of number of protons and number of neutrons. Number of neutrons is in an atom equals the difference between mass number and atomic number. For example, the mass number of fluorine is 19 and atomic number is 9, indicating 9 protons in the nucleus. So number of neutrons is 10. The atomic number, number of neutrons, and number of mass number are all positive integers, whole numbers. Once again, contrary to Dalton's atomic theory, atoms of the given element are not all identical. Instead, most elements have two or more isotopes. Atoms that have the same atomic number, Z, but different mass number, A. For example, there are three isotopes of hydrogen called hydrogen, or you can call it protium, deuterium, and tritium. Hydrogen or protium has one proton and no neutrons in its nucleus. Deuterium has one proton and one neutron, and tritium has one proton and two neutrons. Thus, to represent the isotopes of hydrogen, you write with 1, 1, 1, 2, and 1, 3. They indicate the mass number. The chemical properties of an element are determined primarily by the number of protons and electrons in its atom, not by the number of neutrons. Therefore, isotopes of the same elements typically exhibit very similar chemical properties. Not the same, but very similar. Early scientists didn't have the experimental means to measure the mass of each kind of atom. They succeeded in defining a relative scale of atomic masses. An early observation was that carbon and hydrogen have relative atomic masses of approximately 12 and 1, respectively. Thousands of experiments on the composition of compounds have resulted in the establishment of a scale of relative atomic masses based on the atomic mass unit, AMU, which is defined as exactly 1 per 12 of the mass of an atom of a particular isotope of carbon atom, called carbon-12. On this scale, the atomic mass of hydrogen is approximately 1. You can see exact mass in this periodic table, but approximately 1. That of sodium is approximately 23, and that of magnesium is approximately 24. This tells us that sodium atoms have nearly 23 times of mass of hydrogen atoms, and magnesium atoms are about 24 times heavier than hydrogen atoms. If we know the atomic masses of the component atoms, we can calculate the mass of molecule. The molecular mass is the sum of atomic masses in the molecule. For example, the molecular mass of water is 2 plus 16 is approximately 18. In general, we need to multiply the atomic masses of each element by the number of atoms of that element present in the molecule and sum over all the elements. Then you need values of atomic weight consulting the periodic table. Now, what about periodic table? I think all of you saw this periodic table in your school, maybe, or maybe in college. I don't know. In 1869, the Russian chemist Dmitry Mendeleev and German chemist Lothar Meyer independently published arrangements of known elements that are much like the periodic table in use today. Mendeleev's classification was based primarily on chemical properties of the elements, whereas Meyer's classification was based largely on physical properties. The tabulations were surprisingly similar. Both emphasized the periodicity or regular periodic repetition of properties with increasing atomic weight. Mendeleev arranged the known elements in the order of increasing atomic weight in successive sequences so that elements with similar chemical properties fell into the same column. He noted that both physical and chemical properties of the elements vary in the periodic fashion with atomic weight. His periodic table of 1872 contained the 62 known elements. Now the periodic table consists more than 100 elements. Each element in the periodic table is represented by a tile containing the element's name, element symbol, consisting of one or more commonly two letters, the atomic number, integer, and the average atomic mass, commonly given to 4 significant figures, sometimes more. The elements are arranged in periods, horizontal rows, in order of increasing atomic numbers. The first period contains just 2 elements, hydrogen and helium. The second and third periods each contain 8 elements. The fourth and fifth periods each contain 18 elements, from potassium to krypton and from rubidium to xenon, respectively. Most elements can be categorized as metals or non-metals. One of the properties used to distinguish metals from non-metals is their ability to conduct heat and electricity. Metals are solid at room temperature, except for mercury, usually have a lustrous appearance than freshly cut and good conductors of heat and electricity, and are malleable rather than brittle. That is, a metal can be pounded into different shape rather than shattering then struck. Note that metals occur on the left side of periodic table. In this variant of periodic table, metals is yellow colors. It's metals. Seventeen elements are non-metals. All are poor conductors of heat and electricity. 11 are gases at room temperature, 5 are brittle solids, and 1 is a liquid, is bromine. Note the non-metals occur in the right side of periodic table. In this variant of periodic table, non-metals are this one is blue. No, hydrogen can be also in right side if you write hydrogen here. So sometimes you can see it here. Understand? If you write hydrogen here, it also will be in the right side of periodic table. But because in the first period we have only two elements, hydrogen. Sometimes in some periodic table, especially I see it in Russian periodic table, I don't know how in other countries, you can see hydrogen here and here 2 times. Only 7 elements are metalloids, so name it because their properties are intermediate between those of metals and non-metals. The boron, silicon, and arsenic are examples. Pure silicon Has a lustrous of shiny surface like metal, but it's brittle like non-metal, and its electrical conductivity lies between that of metals and non-metals. And metalloids occur in a zigzag band between metals and non-metals. In this periodic table, this one is a purple color elements. About their appearance, I think is examples of metals, the gold, zinc, copper. This one is non-metals, is an example of liquid nitrogen, the sulfur, is the iodine. And these examples of metalloids, is boron and silicon. Boron, silicon. Vertical column of elements in the periodic table is known as a group. Groups of elements sometimes are referred to collectively to their group number. For convenience, however, some element groups have been given special names. For example, group 1A elements is lithium, sodium, potassium, rubidium, cesium, and francium are called alkali metals. And the group number 2A elements, the beryllium, magnesium, calcium, strontium, barium, and radium. This group. Are called the alkaline F metals. Elements in group 6A are sometimes referred to as the halogens. And elements of group number 7A are known as the halogens. And elements of group 8A are called the noble gases. The elements of group 1B and groups 3B to 8B collectively are called the transition elements or transition metals. The periodic table is a remarkably useful tool that correlated the properties of elements in a systematic way to help us to predict the elements' behavior.